Welcome to The Explainer. I am absolutely thrilled to have you here today because we're looking at something that is honestly, truly awe-inspiring. We are going to break down the sheer scale and the absolute engineering genius behind some of the largest, most spectacular offshore megastructures ever created by human hands. We're talking about massive structures that routinely battle the most extreme elements on the planet. They stand tall amidst towering waves and hurricane-force winds day after day for literally decades.
Okay, let's dive right into this, because this is the fundamental question that engineers had to answer. How exactly do you permanently secure a massive 40,000-ton steel city in the absolute most hostile oceans on Earth? It is a monumental logistical and engineering challenge, and the solution they came up with has, quite frankly, completely defined modern energy production.
Well, the answer to that monumental challenge is the fixed steel jacket platform. For over 70 years, this design has been the absolute workhorse of the offshore industry. When you picture an offshore platform in your head, this is almost certainly what you're seeing. And it's remained the industry standard for a very good reason. It relies on a remarkably simple concept, it's incredibly well understood, and it has a rock-solid, proven track record across thousands of successful installations worldwide.
To really appreciate this, we kind of need to wrap our heads around the mind-blowing scale of these structures. Jacket sizes vary enormously depending on where they're going. So for instance, a small jacket built for a platform in the southern North Sea might stand in about 30 meters of water and weigh a few thousand tons. That's huge, right? But a large production jacket built for the central North Sea, standing in 150 meters of water, that can weigh an astonishing 30,000 to 40,000 tons. To put that into perspective, that is heavier than thousands of elephants, built entirely on land and then just dropped into the middle of the ocean.
Section 1. Anatomy of the jacket.
Now, what's really interesting here is the anatomy from the seabed to the surface. The jacket itself is that massive steel framework sitting in the water. It's constructed from large tubular steel cylinders that engineers actually call cans. These cylindrical cans are rolled from steel plates, and then they're welded end-to-end and cross-braced to form this incredibly rigid three-dimensional lattice framework. It's essentially a massive, highly engineered underwater scaffolding.
And that brings us to the most critical part of that scaffolding, the node. A node is the highly complex, carefully welded intersection where these tubular steel members meet. These specific joints face monumental stress. Over a platform's 25 to 40-year lifespan, they experience enormous, relentless cyclic fatigue loading from the constant crashing of ocean waves. Getting these specific welds absolutely perfect and inspecting them continuously, well, that's absolutely crucial. It's the bedrock of managing the entire structure's integrity.
But the waves aren't the only enemy out there. The ocean itself is literally trying to eat the steel. So how do they defeat corrosion? They use something called cathodic protection. Engineers bolt sacrificial anodes, which are usually made of an aluminum or zinc alloy, directly onto the steel jacket legs below the waterline. Thanks to galvanic action, the salt water actually causes these anodes to corrode preferentially. They literally sacrifice themselves, dissolving over time, just to protect the structural steel of the jacket from rusting away.
Section 2. Pinning to the seabed.
Okay, the installation action sequence is just a monumental feat of logistics. Step 1 is the load out onto a barge. And actually, scratch that. This isn't just a step, it's one of the highest risk operations of the entire process. Moving a 40,000-ton steel structure completely horizontally from a fabrication yard onto a floating cargo barge using hydraulic flatbed trailers, that requires unbelievable precision. Then comes step 2, towing it out to sea and upending it in the ocean. And finally, step 3 is driving the piles to secure the whole thing.
The contrast during this process is staggering. During transport, the jacket lies completely horizontally as it's skidded onto a heavy lift barge. It basically looks like a fallen skyscraper. But once it's out of the installation site, the upending process begins. It is carefully slipped into the water, controlled by cranes and highly calculated flooding, shifting from a horizontal transport position to standing perfectly vertical in the deep water, completely ready for the piling to begin.
So once it's standing upright, you have to lock it down. Think of the jacket like a giant tent frame. To hold it down securely, you need tent pegs. But in this case, the pegs are 50-meter-long steel tubes, up to 2 meters in diameter. And you definitely don't just tap them in. Massive hydraulic pile hammers are lowered onto these tubes, striking them 30 to 60 times a minute. Every single blow from that hammer packs the explosive energy of a small bomb. It violently drives the steel deep through the seabed until the platform is completely, 100% immovable.
Section 3. The topside city.
Now we head above the waves to the top side, which is, for all intents and purposes, a self-contained city. What's truly fascinating here is that this entire city is built onshore as separate standalone modules. Only once the jacket is completely pinned to the seabed are these massive modules transported out by heavy barges and carefully lifted into place on top of the static, non-moving jacket structure by these massive crane vessels.
This steel island essentially relies on 5 vital organs to keep it alive and functioning. First, you have the well bay, which houses the wellheads where the actual extraction happens. Then there's the process area where the oil, gas, and water are separated. Next up are the utilities, so this is your power generation and water treatment. Fourth is the accommodation block, which is the literal hotel where the crew lives, eats, and sleeps. And finally, the helideck, because out there, that is the only way in or out for the personnel.
Section 4. The deep water limit.
You see, ocean waves hold incredible power, and that power actually increases exponentially the deeper you go. Consider the math for a second. A jacket in 30 meters of water might weigh a few thousand tons, but if you move that to 150 meters, the weight doesn't just multiply by 5. It absolutely explodes to 40,000 tons. The structure has to be made exponentially thicker and heavier just to resist the terrifying overturning moments caused by decades of storm waves crashing against it. It is an extreme non-linear curve.
And this brilliantly illustrates the ultimate engineering trade-off. Fixed platforms are amazing because they provide a completely static environment. Things don't move. And that means you can use simple, rigid pipes, which are called risers, to bring the oil up from the seabed. Floating systems, on the other hand, bob around in the water, meaning you need very complex motion compensation and really expensive flexible risers. But because of that exponential weight problem we just talked about, fixed steel jackets hit a hard physical and economic wall. They simply cannot go deeper than about 400 meters.
Which leaves us with a massive cliffhanger. At 400 meters, physics basically dictates that building a fixed steel jacket becomes practically and economically impossible. So what happens when you discover a massive energy reserve where the ocean floor isn't 400 meters down but miles away? How on earth do you harvest that? Well, that requires a completely different approach to engineering, and that is exactly what we are going to uncover in our next explainer on floating systems. See you then.